Hey everyone, sorry about that little glitch. The disk that I saved the videos on got filled up just as I was at this point in the video. So this is part 2. We'll call this linear programming part 2, where we finish up this example of John and Ben raking the leaves and mowing the lawn. So I believe we were right here. We had just sketched the purple line and the blue line, and I was talking about the feasible region being between the two, but we still have green. So it's time to graph the green line now, the last constraint. So we have to start with the y-intercept. Now with this guy, we have the mx right here. The 2 is going to be our slope, but if you remember, when there's no b sort of written behind the mx, you just assume it's plus 0. So we're actually going to start at the origin. And then from there, our slope takes us up to and over 1, or 10 over 5, but 10 over 5 is 2, so we're okay. So up to over 1. I'm going to keep doing that. Up to over 1. Up to over 1. Up to over 1. Up to over 1. Keep it going. Okay, let me just double check I did up, up 2 over 1. Yep, I think we're good. Okay, greater than or equal to, so let's solid line, draw a solid line. And we are coloring greater than or equal to. Okay, put your pencil on the y-intercept down here at the origin. If the y is getting greater, we have to go up. Y greater. So if you think about the line, we got to go up, not down. So up puts us over here. Okay, so now the question is, where do the 3 colors merge together? What is the feasible region? So let me grab an orange. I'm going to use orange for this. Well, here I just see purple. Here I see purple and blue. Here I see nothing. Here I see just green. Up here I see green and purple. Right here is where I see all 3 colors. So this that I'm graphing in orange is going to be my feasible region. Okay. Okay, perfect. I'm going to really darken that in and make it obvious. Okay, next step says, step 4, circle the endpoints of the shaded region or the feasible region. It's kind of like the corners where the line segments come together. So if I'm going to circle those, then my endpoints of the orange region are definitely going to be right here, right here, right here, and right here. Okay, 4 different endpoints circled. Now, step 5 says, find the coordinates of the endpoints of the shaded region. Okay, well, let's start at the top. The coordinates of this endpoint are most certainly 0, 90. And the coordinates of this endpoint, 0, 40. And the coordinates of this one right here, let's see, where are we here? On the x, we're at 30. And on the y, I'm at 60. So 30 on the x, 60 on the y. Okay, so 30, 60. And now the final endpoint. Let's check that out. Uh-oh. Do you see the problem? What's the problem with this endpoint? It looks to me like this point right here doesn't fall on a perfect corner of a box the way the other 3 did. But that's okay. Thank goodness we've studied how to solve systems of equations in this unit. So what I'm going to have to do is, first I have to identify the 2 lines that intersect. It looks like the purple and the green. So I have to find where the purple meets the green, and the graphing method is out. graphing didn't work because it's a decimal or a fraction. So now what I'm going to have to do is use one of my other methods. So let me grab the purple line. Here's the purple line. Actually, let me go back up to the original. Let me go with x plus y. Now what I'm going to do here, and this is legal, instead of being greater than or equal to, I'm just going to put equals because I'm not graphing this right now. I don't need to shade. I just need to find the exact point of intersection. So I'm going to change that back to an equal sign. And the green line, y equals 2x. Now, graphing's out. It didn't work. So now we're down to substitution and elimination method for solving the system. What do you think we should do? There is a better way. I mean, I think there's a clear answer to this since y is already solved for. If we call this the stuff, then we can substitute 2x in for this y and get our answer. So how about if we use substitution and we write x plus, okay, where the y is, we're going to substitute 2x equals 40. Combining these like terms, we have 3x equals 40. And so we divide by 3, and x equals, let's see, grab my calculator here. We could do a fraction or a decimal, but I think a decimal will be fine. 40, can you see that? 40 divided by 3, it's 13.3, 13 1/3 hours. So 13 will go 0.3. That's x. Okay, so when x is 13.3, now we have to find y. So I like to go back to the stuff. So y is going to be 2 times 13.3, which if you can do that in your head or just take your calculator, 13.3 times 2, 26.6. Okay, so my final endpoint of the feasible region, this guy right here, is 13.3 and 26.6. Okay, and it looks like we're coming to the end here. Step 6, plug each of the endpoints into the money equation to determine the maximum amount of money Ms. Callahan needs to budget per year to pay the boys. So now, using these values as my x's one by one, and these values as my y's one by one, we're going to see how much money, at most, maximum, these boys are going to cost me to work on the yard. Okay, so let's start with 0.90. So I'm going to bring this guy down. So let's start with 0.90. Now, let's not forget what this 0 and this 90 means. This means John does not work any hours, but Ben works all 90 hours. Remember that one constraint that said that together they don't go above 90 hours? So this first endpoint is giving all the hours to Ben. So if all the hours go to Ben for raking the leaves and John does nothing, let's see how much that's going to cost me. So my money would be, now remember the money equation right here, 3x plus 250y. So I'd pay $3 an hour for absolutely 0 hours that John works, plus $2.50 an hour for the 90 hours Ben's going to work. And that's going to mean I have to budget. I mean, if this is the scenario, then I'm going to have to budget $2.50 times 90 hours. I'm going to have to budget $225 to pay Ben, basically. Okay, $225. All right, so that's this one. All right, let's go to 0.40. So now let's say John works no hours and Ben works 40 hours. How much am I going to have to budget? Well, money equals $3. Remember, John's not working. And then $2.50 times 40. So $2.50. Oops, you can hardly see this here. Try and keep it in the light. Times 40. $100. Okay. $100 I need to budget. Now let's go to 30/60. So now John's going to start working. So if John works 30 and Ben works 60, then M is, we're going to pay John $3 an hour for $30 or 30 hours of work. And we're going to pay Ben $2.50 for 60 hours of work. How much do I need to budget then? Notice here, like, so Ben's hours have come down, but John's have increased. So 3 times 30 plus $2.50 times 60. I'm going to need to budget $240 to pay the boys. And last but not least, if I use this last guy right here, if John works 13 1/3 hours and Ben works 26 2/3 hours, then the money I have to budget is $3 for each hour, 13.3 plus $2.50 times 26.6. This gives me, one last calculation here, 3 times 13.3 plus $2.50 times 26.6 hours, 106.40. Okay. Now let's reread the question. We wanted to determine the maximum, the most money I need to budget. Well, which one of these is the most? I think we got it right here, 240. So this scenario right here is going to create the most money. And if this is the case, I just want to remind you, this answer right here, the 30 and the 60, I want to show you how that meets all of the requirements of the problem, all of the constraints. Let's go back here. Remember these 3 constraints? Here's what I want to ask you. If X is 30 and Y is 60, let's check that out. Does 30 plus 60 equal something greater than or equal to 40? Heck yeah, it does. 90. So 90 greater than or equal to 40, yes, meets that restriction. Second restriction, do the boys end up working less than or equal to 90 hours? Well, let's see. 30 plus 60 less than or equal to 90. 90 less than or equal to 90. Well, barely. But yes, 90 equals 90, so this is a yes. And lastly, is Y 60 greater than or equal to 2 times 30? Is 60 greater than or equal to 60? Just barely, but it is because it's equal. So that's a yes. Now, what's cool about this is if you really think about the numbers, doesn't it make sense that the maximum money I would have to budget would come when the boys, when their total is the highest it can be, 90. Remember I said they cannot work more than 90. Well, 30 and 60 puts them right at the 90. So that makes sense. All the restrictions are met. Where like if you look at the second scenario, 0-40. Well, 0-40, you add those together, 40 hours, that's the minimum I want them working. So that's not going to produce the most money I need to budget. Now, the 0-90, this guy right here, okay, that is the maximum amount of hours because it's going all to Ben. But remember, Ben was the cheaper bargain. So that kept it slightly under when we had Ben coming on at a higher price. And then if you look at the last one, the 13 and the 26, that doesn't add up to even close to 90. So there's not enough hours going on there to make that the maximum amount of money. So it really makes sense. So it's kind of like linear programming is really taking a scenario where you have certain restrictions, constraints, and meeting those restrictions and finding yourself a feasible region. So basically, any point in this orange area, any guy in here, if John mows that many hours and Ben rakes the leaves this many hours, anything falling in here is going to be okay. It's going to meet my requirements. But at the endpoints is where the magic happens. The endpoints is where you're going to find your highest and your lowest values. So that's why we went to the endpoints to find the most money I would have to budget. Anything on the interior is also going to work. It's just not going to create maxima or minima. All right, thanks for watching and hanging in there through these 2 videos. If you were absent from class, this is really going to catch you up. And now we're just going to practice linear programming. Thanks for watching.